Okay, so now we've got the dependent situation under our belts. Let's look at the independent. So now we've got two independent samples, and the hypothesis we want to test is exactly the same as in the dependent case. So we're looking at the differences between the two population means, and we hypothesize that that difference is delta. And once again, the most common delta we're going to be looking at is delta equals 0, so that there's no difference in these two. So there's no difference between males and females or whatever. Then there's our generic t, just like before. The difference now is going to be how we calculate this standard deviation. Now, let's get some notation. So first we've got population 1. It's got a mean of mu1 and a standard deviation of sigma 1. Population 2 has got a mean of mu2 and standard deviation sigma 2. And what we're going to do is we're going to take a sample from each of these. So from the first population, we'll take a sample of size n1 with a sample mean of x bar 1 and a standard deviation of s1, sample standard deviation. And then sample n2 from the second population. And n1 could be equal to n2, but it doesn't have to be. Whereas in the dependent case, they had to be the same. Now they don't have to be the same. And there's the hypothesis. There's our null hypothesis that we wish to test. Okay, so the obvious t that we could think of probably is to take the variance of the first sample divided by n1, then the second, and average that out and use that as our variance. Now, what we plug in here for these, or whether we go with this at all, is going to depend on another question. So in the independent situation, we're going to ask a second question. And that second question is going to depend very much on what we know about the two standard deviations. We need to know whether the standard deviations in the parent populations are equal or not. If they're equal, we call that the homoscedastic case. If they're equal, then we are going to do the following. Now, first of all, this assumption of whether they're equal or not can be tested, but we're not going to get into that. That's debatable whether you want to test them or not. But if you are in this situation, then what you do is you put s1 squared equal to s2 squared, give them a common value, call it s squared, and here it is. It's a weighted average of those two individual variances, and then your degrees of freedom for your t would be n1 plus n2 minus 2. Now, here we see what price we paid when we had the dependent case. Instead of the independent case, when we had the dependent case, remember in the dependent case, the degrees of freedom, in the dependent case, we took the differences, didn't we? And then we had a sample of size n. Let's say n1 was equal to n2, so just call it n. We had sample of size n, so the degrees of freedom was n minus 1. Now, what we see here is that this, if n1 is equal to n2, for example, this is twice that. So that's what because of the dependence in the dependent case, we basically lost half the power, roughly speaking. Well, we had half the degrees of freedom than we have in the independent case. Now, so in the homoscedastic case, if sigma 1 is equal to sigma 2, this is what you would do. But I want you to look at the heteroscedastic case, when we don't assume that sigma 1 is equal to sigma 2. So even if it is equal to sigma 2, I would still recommend you going with this one, because you lose very little when you state that you'll go along with the formulas for the heteroscedastic case. The complications with the heteroscedastic case is that the degrees of freedom, call them nu, get to be a little bit more complex to calculate. But that shouldn't bother you, because you're not going to do these calculations anyway. Stata is going to do these calculations for us. But there's the formula, just to make you feel good. So the recommendation is just go with the heteroscedastic case. So let's go off to Stata and see how easy it is to actually do these calculations. Okay, so now let's see what we can do in Stata for the two-sample independent situation where we want to do the t-test. So let's look at our variables and see what we have here. Oh, okay. there's an idea. Let's look at the hypertension situation. So let's tabulate hypertension, and let's look at summarize the total cholesterol level at the first visit for these two groups. Okay, so we have that the difference in the mean in those two groups, for those who don't have hypertension, their cholesterol level is roughly on the average 228, whereas for those who did have hypertension coming in, their cholesterol level is about 240, a little bit more than that. So now suppose we know this because it's the population, we know the population, but suppose instead of that we took a random sample, and let's see where that would lead us if we didn't know the whole population but only knew a random sample. So let's set our seed again, so in case we want to redo this and get the same numbers. So this isn't really okay, so there it is. Now let's take a sample, let's say a sample of size 49, and let's say we want, okay, but let's get one from each. So sample size 49 from each. So we'll do that by hypertension. There we have it. So now let's take a look at what we have in our sample. What do we have? So in our sample now, we have 48. So we lost one because there was missing data. So of the 48 who do not have hypertension, their mean is 220. And for the 48 with hypertension, their mean was 236. As opposed to in the population, this is what we had. And the standard deviations are pretty good estimates in the sample of what they were in the population. Now, we go to statistics, summary tables, and the classical tests of hypotheses. And what we want is the two sample mean. So classical test of hypotheses, we want the two group mean comparison test. So there it is. The variable that we want to test is going to be our total cholesterol level at time 1. So it's TOTCHOL 1. And the group variable name, that was hyper10. And that's it. So now, are we going to assume equal variances or unequal variances? Recommend you click that at the unequal variances. Now, I didn't mention this before, but the approximation that you saw in the previous clip, that was called a Satterthwaite approximation. There's another one you could use, which is Welch's approximation, and you would get that if you clicked this. They give you very similar answers. What you could do, of course, is run both and see if there's any differences. There shouldn't be any differences. Let's see what this does. So here we go. Now, let's look at the output. So put that aside, and let's look at the output. For the first group, the mean was 220, as we saw before, and for the second group, the mean was 236, as we saw before, and the combined mean was 228. Now, here's the differences. If we look at the differences, then that would be 220 minus 236, etc. There it is, 15.375. Those differences have a standard error of 8.81. And if we want to use the confidence interval approach to test the hypothesis of any differences, we would find that the 95% confidence interval goes from minus 32.88 to 2.13, which includes the value 0. So by using the confidence interval approach, we would not reject the null hypothesis that the two means are the same. Let's see if the hypothesis testing approach gives us the same answer, as it should. And the answer is yes, there it is. The p-value, when you test a hypothesis that the difference is equal to 0 with the alternative two-sided, then the p-value is 0.0844 based on this sample of size 48 and 48. Now, that's 96, and remember, if we just take off 2 degrees of freedom, so that would give us 94. Satterthwaite's approximation gives us a 93 degrees of freedom. Not that different. Had we done the Welch's, probably we would get the same answer. But this is how we read the result of our command, which was to say t-test. So t-test on the total cholesterol, by, there's the two groups, hyper 10, and let's not make the equal variance assumption. So you have to say, I'm going to make the unequal one. I leave it to you to explore what happens with the Welch approximation, to explore what happens if you use the equal assumption.